Hey guys, welcome back. So today I'm working on this Honda EM500. Now this machine I've actually already made a video on. A subscriber had sent it to me when it stopped producing the correct voltage. Instead of 120 volts, it started producing close to 200 volts. So that first video was spent mostly troubleshooting what had gone wrong and ultimately determined it needed a new AVR. Now, normally that's an easy fix, but because this machine is about 40 years old, that AVR was discontinued. Thankfully I was able to locate a new old stock AVR. The only issue was it was $200. And as far as I can tell, it was the last one available because I have not been able to find one since, and a few people have reached out looking for an AVR for this machine. So my hope is to come up with a prototype of an alternative board that can power this machine. And to that end, a few of you who watched the original video reached out and offered to depot the bad AVR and reverse engineer it. So I thank everyone who came forward with that offer. I could only choose one person, and that person's name is Bill. I sent him that board within a few weeks. He had it fully depotted. He had a rough schematic drawn up, and he's come up with a few alternative designs. Now, before building the prototype, I need to gather more data because although I did hook up a bunch of meters to the outputs and supply power to the field with a lab power supply, I didn't put the generator under load, and I don't know how those numbers are going to change based on that. So what I need to do here is get all these tins back off. We'll get the AVR out. We'll install this adapter from the old AVR where we can probe and measure what we need to. And once we have that data gathered, I can build a prototype and potentially come up with something that I can offer people to get their machines up and running again. So let me set up a little bit better and get going on this. I'm going to take a second and just extend these wires. This is the only adapter I have, and there's not a lot of wire on there, so I'd feel more comfortable, I guess, having more wire to work with, and I'm also going to stagger the wire lengths just a bit to minimize the chance of anything shorting out during the test. So I jumped ahead a bit. These wires were extended. I now just have this piece of plastic underneath to help insulate against the metal table. Now the plan is to get the engine started, we'll double check the speed. I want it running at about 62 hertz. And then I'm going to bring the field voltage up until we get 122 volts out. So in order to do this, I need to first set my limits. I'm going to set this at an amp. We'll set the voltage at about 6 volts and we'll go from there. Now, the current is going to flow through here so we can get a more accurate read on the current. And I'm also going to use that meter to check the voltage going into the field. Now, the power supply does have its own gauges, but I've found those seem to be a little bit off. So these meters will just serve as the double check. So once this machine is running, we'll do what we need to do to get the output voltage up to 120 volts. The output is connected through the kilowatt, and it's also connected to 6 lights over there, which will bring it up to just past full load at 420 watts. We can also double check the voltage output using this meter versus the kilowatt. And then we have these 2 meters here. The one on the right is going to measure the excitation winding, and that's also going through a 100 ohm resistor, which will simulate the power requirements of the voltage regulator. And this meter is connected to the sense winding. And this is what the regulator uses to monitor the output and make adjustments to the field based on what it sees. So let's rig up a fuel supply. We'll get it started, let it warm up a bit. I'll tune that speed to about 62 hertz. We'll bring the voltage up to get 120 out. And then I'm going to put it under a full load or just beyond and adjust the field voltage to see what's required to maintain 120 volts. I'm then going to shut it down. We'll reset the test. And I want to do another test, which I'll talk about in a minute. But for now, let's just run this test and see how it turns out. So what I'm going to do on this power supply is just limit how much voltage and current it can provide to the field. So right now we're right around 3, maybe 4 volts. And I know we can bring that up a bit closer to 6 without any worry. And then to set the current, you actually have to short the leads out. And right now we're pulling about 1.6 amps. So I'm going to back that off to about an amp. And it's actually less than that. This gauge is not completely accurate. According to this meter, we're at 0.898, and that seems to be more accurate. I've tested this with several meters, and they all agree that this is not correct. So with these settings, we should be pretty safe to start that generator and power the field without worry that we're going to cause a meltdown. I think the hard part's going to be starting it without knocking any wires out or creating a short. So according to this, we're at 4 volts DC, about 0.2 amps. And the meters here closely agree. We're at 0.172 amps DC, 4.37 volts on the input. And on the output side, we're at close to 120 volts. The sense winding, we're at 19 volts about. And on the excitation winding, we're at 15.9 volts. And according to the kilowatt, we're at 119.4. And if we take a look at the watts, we're currently pulling 0 watts. So let's turn the load on. And you can see the lights just got pretty dim, so I'm guessing the voltage is quite low. Yeah, we're down to 60 volts actually. According to this, only 130 watts. So let's bring the voltage back to 120. There we go, we're at 120.2. We're now supplying 0.46 amps, almost 12 volts DC input to the field to make this happen. The sense winding, we're about the same, 18.8, and the excitation is 18.86. Now we're pulling 356 watts, so let's turn the last light on, which should bring us over 400 watts. And we're actually not, and I'm guessing that's because the voltage dropped. So let's bring this up a little bit more. So now the field is pulling 0.58 amps. We're at 15.1 volts DC input to the field. We're back to 120 volts. And the sense is pretty much unchanged. And the excitation might be up a little bit at 19.4. And we are now pulling 426 watts. So I think I got the information I need. I'm gonna have to turn the load off and actually bring the voltage down on the field because it's gonna end up blowing some lights if I don't. I brought it down to about 108 volts. Turn off a few more lights. Now we're up to 130, so bring that down a little more. And people wonder why I use this cheap meter instead of a better one. And really the answer is the results from this meter aren't bad, at least for what I'm doing. And more importantly, this meter does not shut off. It'll stay on for days or weeks until I shut it off. And that, for me, is important because in the middle of the test, that shut down. This expensive one shuts down. These two have since shut down automatically, even though they're still in the on position. And this one's next. It also has a timer. So that is a big deal. Anyway, as far as the testing goes, I got the data I need. And unfortunately, it kind of makes the second test a little bit pointless because instead of an automatic voltage regulator, I was really hoping that I could get away with just a voltage regulator, meaning set the no-load output to 130 volts, load it to the max, and the voltage would drop but stay above 110 volts. And based on what I just saw, I don't think that's going to happen because we started at 4 volts to the field, and under a full load, I had to bring that up closer to 16 volts. So I think if I just set the no load voltage at 130 and then bring the load up, the output voltage is going to quickly drop to below 110 volts. So I'm going to double check that. We'll see how much of a load it can support before we drop below the minimum. But I think the simple replacement that I was considering is not going to work. It's going to have to be an automatic voltage regulator, but let's make sure. So we're putting 5.5 volts in, about 0.2 amps, and we're pretty close to 130 volts. Let me bump that up just a bit more. And it is fluctuating a lot, but now we're just a little bit above 130 volts. And let's see, this is the sense, 20.8 volts. And the excitation, we're at 17.1. So let's turn on one light. And see what that does to the output. So you're already down to 114 volts. So that's too low for just a 70 watt load. Let's double that to 140 volts. The output's holding at 110. Let's try one more light. And now we're too low. We're at 98 volts on the output. The kilowatt agrees. So yeah, that is not gonna work. So as feared, applying a fixed voltage to the field, it's not going to be adequate. I could only turn on about 2 lights before the voltage dropped to 110 volts, and turning the third one on brought it down to 98 volts. So a fixed voltage regulator, that's crossed off the list. We need an automatic voltage regulator. So let me send these results to Bill, and I'll pause it for now, and I'll get back to you in a bit with the plan. I showed the results to Bill, and he agrees. A standard voltage regulator, it's not going to cut it on this machine. We need an automatic voltage regulator. So he finalized the design to build an automatic voltage regulator, and he also included a parts list. And I ordered those parts from DigiKey. They showed up today. We have enough parts to build at least 2 complete boards, which is a good thing because I have no experience building boards. And chances are I'm going to need those parts in order to get one functional board. So I'm not going to record this build in detail. I want to focus in on the task at hand. Of course, I'll turn the camera back on, show you the end result, and give it a try. Well, there's a look at the end result. It took quite a bit longer than I ever anticipated. And I've got to say, although I'm sure the design is good, my abilities to put this together, I think, are in question. I have no experience doing this, and yeah, let's just say there's a reasonable chance I could let the magic smoke out. But yeah, I'm hoping for the best. Anyway, I'm going to spend a few minutes, actually more than a few minutes, double checking my work, and if it looks good, we'll plug it in and see what happens. The board is wired into the generator and ready to go. So either this is going to ruin my day or make my day. And hopefully it doesn't ruin the generator. So I did add a couple of inline fuses to help protect it in case things go horribly wrong. So these are rated at 3 amps. I've got one on the sense winding as well as the DPE winding. So assuming it starts and produces voltage, hopefully it's around 120 volts. There is a potentiometer on the board to adjust the voltage. So if it's off, we'll tune the voltage if we can to 120 volts. And assuming that goes okay, we'll start to load the generator up. I've got 6 70-watt lights here, and when they're all turned on, that'll be 420 watts, which is just over the max rated of this machine. So let's get it started and see how it goes. And I'd be lying if I said I wasn't a little bit nervous. It's trying to tell me something. $140 volts. Not too bad. We're at 142 volts. Let's see if we can adjust that down a bit. We're adjusted all the way down on the potentiometer. So it stopped at 125 volts, which is fine. That is a normal acceptable range. So let's start turning a load on. Let's start with 2 lights. So that's 140 watts. And we're holding steady, 124.2 volts. So it came down a little bit, but it's still good. We'll turn on 2 more lights. 280 watts. And we're holding just fine, about 123 volts. So let's turn on 1 more. 350 watts. And we're at 121.8, which is good. And now we'll overload it just a bit. If the engine can stay running. We're at 420 watts. And the voltage is fine at 120 volts. Let's double check what the hertz are at. Actually a little bit slow. We're at 56.5. So let's take the load off. Potentially we need to adjust the engine speed a little bit. And without a load, we're actually at about 62 hertz. So that is fine. So I would say that was a good test. I've got to admit, I imagined so many ways that this was going to go wrong, and I was just waiting for that magic smoke to come out, and it didn't. Instead, the board powered up, it sent power to the field, and we had 140 volts output. So I adjusted the potentiometer, brought the voltage down to 125 volts, at which point I maxed out the travel of the potentiometer. So we do need to make a little adjustment down here, most likely swap out one of these resistors to center that a little better. That said, for a small engine like this, you want to have the voltage a little bit high as well as the engine speed. So 125 volts was actually a pretty good place to start. So we loaded it up, brought it past the max to 420 watts. And at that point, the engine was actually losing speed. We were down to about 67 hertz. The voltage, though, was holding at 120 volts. So we only had a droop in voltage of about 5 volts from no load to full load. So this design is doing a very good job, and I can't take credit for it. Bill spent a lot of time planning this out, and I only put it together. So yeah, not too bad. Anyway, this is not going to fit into there. The point of it was to prove the design. The next step is to get it into a package like this. Now, Honda did use a few less components. That said, the component count is pretty similar. So they went to a pretty great length to fit it all in here. And that's where I'm going to end it for this video, because I know some of you design PCBs for a living and could probably make quick work of this. So the goal is to get someone to come forward, design a PCB that'll fit the components needed. And then we can have some printed up. We can build some by hand like this and test them out. Now that I wish was the end of the story, but I'm also having a problem finding this connector. Without it, anything we build is not going to plug into this machine. So I haven't ID'd it yet. Most likely this is a connector that Honda used on their bikes. So if someone recognizes it and knows where to get it, let me know, because we're going to need some. So I hope this video helps someone. Thanks for watching. Not quite done yet. If you made it this far, you might be interested in what I'm about to do. I did send the video link to Bill. He was happy that the board worked, but he was a little puzzled as to why I had to turn that potentiometer all the way to one end to get to 125 volts. So there's a few possibilities here. One, and probably the most likely, is that I wired something wrong. The other issue might be with the data we gathered, because I used a lab power supply to power the field, and from that we got data on the sense winding as well as the excitation winding. And we put this load on the excitation winding to simulate the power that this board was going to use. And I think an oversight there is that this excitation winding also powers the field, about 9 watts. So I think the results on the actual board are going to vary based on how we tested it back in the beginning. Also, the sense winding we didn't load at all. So this board, the logic on here does use a bit of power, and that's going to affect things as well. So I've already updated my data, testing a bunch of different points with the multimeter, and thought you might be interested in what I'm going to do next with the oscilloscope. I want to look at the waveform on the output for the MOSFET as well as the voltage regulator. Right now I am connected to the MOSFET, and the way this controls the power to the field is that it pulse width modulates the output, meaning it's not going to send the full 20 volts to the field 100% of the time, because if it did that, we would have 200 volts output. And that's where the logic comes in. Based on the generator load, it varies how long that power is output to the field. So without a load, it might only be turned on 20% of the time, and under a full load, maybe closer to 80%. So that's what we should see over here. At DC voltage, it is represented by a straight line. When that MOSFET turns on, you'll see the voltage go up. It'll look like a square wave, and then it will come down. And the longer the MOSFET stays on, the wider it'll be represented on here. So once this gets powered up, I'm going to use a variac and just bring up the load slowly. And we'll see that duty cycle increase and decrease. And we'll get a good look at the waveform. So we'll do that first. Once that's done, we'll move the probe over, test the linear regulator on the input and the output, and see what that looks like. Just going to adjust this to make it a little bit more readable. There we go. So I've tried to set this up in such a way that it makes a little bit more sense. When it's at the bottom here, that's essentially when it's off. And at the top is when it's outputting voltage to the field. So right now we're at 121 hertz. And you can see the duty cycle, it's pretty narrow. So it's on, I would say, about 20 to 25% of the time. So I'm going to turn the variac on. I'm going to bring the voltage up close to 400 watts. And as the generator loads up, we should see the width or the amount of time that this MOSFET is on increase closer to 50 to probably 80%. So I'm going to turn the variac on. We're at 378 watts, about 125 volts. And you can see it's now on quite a bit longer to maintain the 125 volts. Now it is interesting though, kind of what's going on here. It's almost like the MOSFET shuts off, but then something happens here. I'm not sure if it's completely shutting off right until the end. So that's something we'll have to look at. So we'll just take a couple pictures of that. Now I'll take the load off slowly. For this test, I've moved the oscilloscope over to the linear voltage regulator on the input side. Now this one should look fairly flat. There will be a ripple of about 120 hertz, and that's expected. What I want to see is just how bad that ripple is when there's no load versus a full load. So we'll get it started, just capture that data, and then move to the final test. And there you can see the ripple. It's actually so small it's not being picked up. Let me switch this to 1x. And we'll switch that to show 1x. It should show a little more detail if we're lucky. Yeah, it can now detect the frequency. Kind of fluctuating. I'm sure it's just this cheap meter, but it's around 120 hertz. I'm going to take a screenshot of that. Okay, and then I'm going to apply a load like last time. I'll turn the variac on, bring it up to 125 volts. All right, we're at 125.9. We're at 383 watts. Just try resetting that. Take a couple screenshots here. And we're at 5 volts per division. So it looks like it is fluctuating up and down. I'd say somewhere between 8 and 10 volts, if I'm reading this right. All right, I think that's enough data. Now I'm connected onto the output of the voltage regulator, and we should see a very flat line. We don't want to see any ripple here. So according to this, the output is 12.1 volts DC, which is why it's a straight line. And it looks like there is no ripple. Let's load it up. And we're exactly at 12.1 volts. I don't see any ripple to speak of. So just screenshot that. And screenshot that. Well, guys, I think that's really it this time. We gathered the additional data, and most likely there will be a revision B to this board. You know, that said, revision A, it's performing pretty well. You know, we're at 125 volts. We can load the generator fully, and the cost to build this really isn't that much. The parts cost was about $15. Of course, it was about 4 hours of my time. You know, I'm sure someone who knows electronics better can build this much faster and probably cleaner than I did. You know, that said, it is getting the job done, and it's a lot cheaper than spending $200 on the OEM Honda one, which you can't even buy anyway because they are discontinued. So, I hope this video helps someone. Thanks for watching.